Okay, so far we have discussed basically vapor power cycles, right? I hope you have gone through the lectures, and this point onward we will be discussing about gas power cycle. So let me quickly draw our roadmap here, right? So basically we have engines, right? Engines, heat engines. Then under there we have gas power cycles, and then we have vapor power cycle, right? So under there we have discussed Carnot cycle, Carnot vapor power cycle, and then we have discussed Rankine cycle, right? This part is covered. So but today's plan is to discuss about Carnot cycle and then Octto cycle. Then we have another one, diesel cycle. Okay, so that's what we're going to do, right? So why we call this one as a gas power cycles? Basically because throughout the cycle the working medium or the working fluid remain its gaseous form. That's why we call it as a gas power cycle. Then vapor power cycle, if you remember, vapor power cycle we have phase change. Sometimes it's changing liquid to gas, then again gas to liquid, like so there are phase change. That's why we call it they as a vapor power cycle. And gas power cycle, throughout the cycle we have gas in gaseous state. Working fluid remains in its gaseous state, right? And oftenly we study the ideal cycle in here, right? Because normally we study we omit all the irreversibilities and complexities. That means basically we remove all the the heat losses and friction losses likewise, right? We basically omit those things, and we work with ideal gases, right? So if you look on a PV diagram, what actual cycle, right? What ideal cycle is look like this, right? So this is what you see, right? In idealized cycle, right? This idealized cycle, right? But in actually it is not like that, right? In actually actually it is not like that. So this is the actual cycle, right? Because we can't actually work on the actual cycle as it is, right? But what we normally do is, what we practice is we work on idealized cycle, then use coefficient to transfer it to fractions to transfer it to actual cycle, right? So you can see these sharp turns. Normally you can't find these sharp turns in actual cycles, right? But idealized cycle you can find, we can construct like this, and then we can extend that one to actual cycles later on, right? But of course in our scope we are not dealing with actual cycle, but mostly on idealized cycle, right? Okay. So I hope you remember the heat engine. The efficiency for the heat engine, you can we can say neta equal to W net divided by Q in, and W net, if you remember, W in minus W out, right, divided by Q in. So this is what our efficiency is, right? So with that, let's we discuss about the Carnot engine. Now we already discussed about the vapor Carnot engine. So this is the gas Carnot engine, right? So again, as you have learned in the previous time, Carnot engine is a theoretical construct, right? And of course you can't find any application of Carnot engine, right? In real world we can't make a Carnot engine, right? It's basically a theoretical construct, and it is the engine where the maximum efficiency is achieved, right? If it is a Carnot engine, that is the maximum efficiency you can achieve in any kind of engine. That means in a real world engine there's no engine that can beat the efficiency of a Carnot engine. That's what it is mean, right? So and in this engine we are talking about something like this, right? So this engine is basically a piston cylinder assembly. So right, so you have a piston, so you have piston here, right? Likewise, so this is the cylinder and you have the piston, right? So the piston, and this cylinder wall is not conducting heat, right? And there are no heat transfer in this in these walls, and this cylinder goes up and down, and the cylinder is also frictionless. There's no friction forces, there are no heat losses, right? And if we denote something like this, let's say this way, Q in, right? So this means heat enters inside the chamber. If it is something like this means heat out, heat goes out from the chamber. That's what this means, right? And also we assume this work on two temperatures. We have a heat sink and heat source, right? So let's we assume we have three block, right? So this heat source, let's we denote as the temperature TH, high temperature, and we have heat sink, right? Sink, that means low temperature TC, right? And we have another called isolation block, right? This is isolation block, right? Okay. Now this is what basically the cycle is, right? Now we have the piston cylinder assembly. So this is the cylinder, right? So this cylinder, now these walls are not conducting any heat, right? This side and this side, okay? And we have the piston. This piston can move up and down, right? And we have a gas here inside the cylinder, and we have three blocks, right? One for the heat source, another one for the heat sink, another one for the isolation block. So that is what here. So you can basically interchange this one, right? You can plug isolation box, or you can plug a heat reservoir or heat sink, whatever things, to the bottom, right? So this part can conduct heat, right? That means if you plug a heat source, it can transfer heat into the inside the piston cylinder assembly, likewise, okay? Right. Now this gas is ideal, right? And also we don't have any friction losses or heat losses in here, right? Now let me assume three positions. So let's say this is position 1, let's say position A, and somewhere in B, and somewhere in here C, right? So the position A is the fully extended position, and B is somewhere in between, and the C is the fully compressed position, right? Okay. Now let me start from the middle position, that means point B, place B, okay? Right, and the same time we will draw the PV diagram for this one, right? So P and V diagram, right? Now this one work on two temperature, therefore we have a TH and TC. Now let's we draw the temperature line. So this is our first temperature line, which is TC, and we have another temperature line here, let's say TH, right? TH, okay, right? So now assume our piston is in position B and we have a gas here, right? Now what we're going to do is we apply a force, right? Apply a force and compress it, right? Now think we have at point B, and our temperature is TC, right? Somewhere in here, right? Somewhere in here, right? Temperature of the gas is at the beginning of the compression. Let's say assume it is TC equal to our temperature of the cold reservoir, right? Then what we're going to do, we apply a force and compress it. Now what will happen? Now there's no heat transfer in this wall, therefore you are only doing work, there's no heat transfer, therefore you can categorize this one as adiabatic compression, right? No heat involved, only work, right? Now if you remember in the first law of thermodynamics, right, delta U equal to Q minus W, right? No Q, this is 0, right? No heat transfer, but the work is involved, therefore your internal energy increases. When you compress it, your internal energy increases. That means temperature increases. When you compress this piston, your temperature in gas increases, right? Okay. Now we compress it until it reaches the temperature to TH, right? That means you are compressing it, and this is adiabatic compression. You are increasing the temperature such a way that temperature goes to TH, right? That's 1 to 2%. Okay, right? Now in here we have isolation stand. That means there's no heat supply or heat extract, therefore there's no heat involved, only work is there, therefore the internal energy increases. That means the temperature increases, right? Now what happened? Now we have compressed it. What happened if we remove this force? If we remove this force, right, what will happen? It will come back. Now this goes like this, right, up to here. Then if we remove this force, then it will come back all the way back to here, right? Okay, that's okay, no? Right. But instead what we're going to do is, right, we remove this insulation sand, right? We remove this one and plug a hot reservoir, right? Keep the hot reservoir and remove this force, right? Then what will happen? Start moving upward, start expand. When it expand, what will happen? Temperature decreases, right? Temperature decreases, but then what happen? You have temperature difference, right? Now when the temperature start to decrease, when this moves up, at that time you have temperature difference, therefore heat can flow. Since there is a temperature difference, heat will flow inside this chamber into the gas such a way that it will reach the temperature TH, right? That's mean what is happen? This will expand, and the same time heat will go in, but the temperature will remain on the same TH, right? Therefore we call this one as the isothermal expansion, right? Because temperature is keep constant, therefore we have isothermal expansion in here. So the volume is increasing because it's expanding, and the temperature is the same, right? Because we have Q in, keep the temperature at the same level, therefore we can say this one is an isothermal expansion, right? Up to some point like this, right? Okay. Then when it come to some point, right, somewhere in the middle, okay, let's say B, somewhere in the middle position, right? Then what we going to do? We can again change the hot reservoir into a insulation sand. We remove the hot reservoir, plug the insulation sand. At that time what will happen? We still have energy in here, therefore they expand further, and the temperature of course goes down because there is no Q in, heating, therefore temperature goes down, right? So we allow it to expand until the temperature goes to TC, right? That means expand in such a way, okay, until it comes to TC, right? Then after expanding to TC, then again what we going to do? We change back the insulation stand to coal reservoir. We plug the coal reservoir, then apply force, and then compress it. So what will happen when you compressing it? When you compressing mean is start to increase the temperature, which means increase the internal energy. That means increase in the temperature. So again you have temperature difference, right? So the temperature in here will be increasing larger than the Tc, therefore you have temperature difference, so therefore you can see a QC. That means your heat will be transferred to the cold reservoir, right? So you are compressing it, volume reduced, but the temperature is same, right? Temperature is keep Tc, therefore this will goes like this. Therefore we can say this one as isothermal compression, right? So there are 4 processes, right? You have adiabatic compression 1 to 2, then you have isothermal expansion, then adiabatic expansion, then isothermal compression, right? So this one is compression, this one is compression, this is expansion, this is expansion, right? That's mean right, that's mean, so this is the compression, again compression, compression. In here we get W in here also we have to do work on the system, right? That means work on the system, that means we have to do work on the system. In this case we have W out and also W out in this case, right? So we have W out in this process and this process, we have W in this process and this process, right? And the Q in, here we have Q in and Q out, heat in and heat out, right? Okay, right. So that is the PV diagram that I have drawn earlier, right? So this basically 1 to 2 is adiabatic compression, right? So this is the W in here you have W in, right? Then in this case we have W out. At the same time we have Q in, right? Q in. So this is isothermal expansion. Then we have adiabatic expansion, right? Also we have W out, right? There's no Q involved here, and in here we have W in. This is isothermal expansion, and this is adiabatic compression. So this is adiabatic compression. Sorry, isothermal compression. So this is isothermal compression, adiabatic compression, isothermal expansion. Adiabatic expansion. So isothermal expansion, then adiabatic expansion. Okay. Right? Then this one Q out. Okay. Now you can see in this case W in, Q out, and W out, Q in. In here W in, W out. So the problem is, does this convert heat into energy, heat into work? Yes, of course. You can see this area is basically the work out, total net out, net W out. Okay, this area is the net W out. Right. So then what is the Q in? So this is basically Q in. If we draw the 2 and 3, so this, all of this is the Q in, right? And this is the Q out, this is the Q out, all of this is Q out, and this is the net work out, okay. Right. So the same thing we can draw it in a TS diagram, right? Enthalpy versus entropy, so temperature. So this temperature is entropy diagram. Then so this is the isentropic compression, right? Isentropic compression. So this isentropic compression. So this isothermal expansion, right? And then this one isothermal, so this isentropic expansion. Sure. Then here we have isothermal thermal compression, right? Why isothermal? Because the temperature is constant. Isentropic, right? Isentropic compression means the entropy is constant, right? So you can see the entropy is constant. Entropy is constant in here, right? Both isentropic compression, isentropic expansion. Then we have isothermal expansion, isothermal compression, likewise. Okay. So that is the TS diagram. So this is the TS diagram, and this is the PV diagram for the Carnot engine. Right. Then let me derive efficiency. For the efficiency, so the same way we can so you can see this the network out, right? And the TS diagram, if you remember, the area under the TS diagram represent the total heat absorbed or rejected. Therefore this is the total heat, right, converted into work, right? So this area, right, what is the representing by this area equals to the area represented by this one, right? Okay. Therefore we can say area therefore we can say like this, right? Area under the PV diagram, right? The integration, basically integration means the summation of area, right? So integration of the PV diagram should be equal to integration of the TS diagram, right? And also it should be equal to this, right? How this can, how we can say like that is so this is the total Q that converted into work, right? So this is the total work out. Therefore total work is the basically the area of the ABCD. Therefore we can write W out equal to this area, that means TH minus TC times SA minus SB, right? So basically this area, right? That is what is in here, right? In here, and that is the total heat that converted into work, right? Then also we can write the total energy transferred from the hot reservoir to the system will be TH times SB minus SA, right? If we go back and see, so that is the, so this is where the Q in, right? Q in A to B. So this is basically the Q in, right? This is the Q in, right? All of this is the Q in. Therefore that is equal to TH times SA minus SB. So this is the Q in, and we can say Q out. So this is the Q out, right? This is the Q out. Okay, this is the Q out. This is the Q out. Therefore we can say Q out equal to TC times SA minus SB. Okay. Therefore this is the QH, Q in, Q out, right? Therefore we can say W neta equal to WOH. W, right? W means the total the network, right? W net, we can write Q in minus Q out. Why? Because the difference is converted into work, right? Then divided by QH, right? And we can Q in, right? And we can write this one 1 minus Q out divided by Q in, right? For these terms you can substitute from these terms, right? Okay, QH, Q in and Q out. Therefore if you substitute this one, this terms goes off, then you can end up with something like this, right? 1 minus TC over TH. Okay, so what this means is the efficiency of the Carnot engine is equal to 1 minus high temperature divided by the low temperature. Sorry, low temperature is the low temperature divided by the high temperature. Okay, that is the neta. Right. Then we have a problem. I want you to take some time and work it on this problem. Let me work it this problem. There's another problem. So problem number 2. It's something similar to problem number 1. Of course, you can work this on your own. But let me start on the problem number 1. Carnot heat engine shown in figure below receives 500 kilojoule of heat. That means Q in. You can say Q in equal to 500 kilojoule. heat per cycle from a high temperature source at 652 Celsius and reject heat to a low temperature sink at 30 Celsius. Determine the thermal efficiency of this Carnot engine. Okay. So let's start with the A. We know neta thermal equal to 1 minus Tc divided by Th, right? So this is equal to 1 minus temperature of cold reservoir is 30 plus 273. What is this 273? Of course you need to convert into Kelvin, right? Not in Celsius. When you apply this equation, the Tc and Th value should be in Kelvin, right? Divided by Th 652 divided by 270 plus 270, right? So you can work on the maths, you can find the neta value, right? Then B, the amount of heat rejected to the sink per cycle. So once you know the neta, right, so the neta is the efficiency, basically the working efficiency. So the heat rejected to the sink, you can derive the equation. So what is the heat received is 500 into 1 minus neta is the heat rejection. So this is the heat rejection, right? So that is the answer for A and B, right? Okay, so this one you can work it your own, right? Let me continue on. So the reverse Carnot cycle. So this one is okay, right? So this is the Carnot cycle, right? So in the Carnot cycle, we have gone 1 to 2 in this way, right? 1 to 2. So this is basically isentropic compression, right? Then 2 to 3 isothermal expansion, 3 to 4 in isentropic expansion, right? Then 4 to 1 isothermal compression, right? So we go on in clockwise, right? Clockwise direction, right? This way, okay? But if you can remove, reverse this one, that means instead of going this way clockwise, you can go anti-clockwise this way, right? Right? That means instead of going this way, you are going this way, right? This way and this way, here to here and there, right? Now what will happen at that time? Now in previous case you have Q in here, so these were the Q in, right? And this is the Q out. So basically you have the hot reservoir here, hot reservoir, and this is the cold reservoir, right? That means you are extracting heat from hot reservoir and transfer to cold reservoir, right? That means the normal Carnot cycle. What happen if you reverse it, right? Instead of, now last time we have Q in like this, right? Q in become a Q out, right? Okay. Okay, sorry about that. So now what happened if you reverse the cycle, right? So what we had previously is, so that we have hot reservoir here, right? Hot reservoir transfer the energy here, Q in. Now instead what happened? We are transferring energy in this side, right? That means we are extracting energies, extracting heat from the cold reservoir, right? So we have cold reservoir, extracting from the cold reservoir, then dumping into hot reservoir. Okay? So this is what exactly happened on refrigeration cycle, right? Whatever the refrigerators, air conditioners, freezers, this is what happened, right? That means you are extracting from the cold body, and again transfer that into hot reservoir, right? But of course we will discuss about this one about in later on when we discuss about the refrigeration cycles. But just for the time being, so there is something called reverse Carnot cycle, right? If you reverse this process, your heat flow reversed, right? Okay. So that's about the Carnot cycle. Now we are going to talk about actual cycles, right? The applications. But before going into that, let me discuss about some of the terminologies of the reciprocating engines, right? So this is common for most of the engine. Either if you look in a petrol engine, petrol vehicle, diesel vehicle or diesel engine, you will find these terminologies, right? So what basically you have in any kind of engine, any kind of petrol engines, you have piston. So this is the piston, and you have cylinder. So this is the cylinder, and the piston assembly, right? Then you have connecting rod which connect the piston and the crankshaft, right? So the crankshaft rotate. When the crankshaft rotate, piston moves up and down, right? That's the basic idea, right? Then you have intake valve. That means the intake air, basically the air plus air fuel mixture, right? Air plus fuel coming through here to the piston, to the cylinder, and the exhaust gas goes out from the exhaust valve, right? So you have the intake valve and the exhaust valve. Then you have in here you have the intake manifold and the exhaust manifold, right? Okay. And these valves, of course, they can open and close, right? Then the piston travels, let's say this part we call this cycle bottom dead center. That is the most down position you can have, right? The most down position you can have we call the bottom dead center. Then the most up point we call top dead center, right? So top dead center and the bottom dead center. So in between that we call it as a stroke, right? Now you may have familiar with the 4-stroke engine and 2-stroke engines, right? But of course in this case we are study on 4-stroke engines, right? So 4-stroke engine means you start from here to there 1 stroke, again from here to there another stroke, again to here another stroke, again to there another stroke. Here we call 4-stroke engine, right? If it is 2-stroke, you start from here, going back here, and start from there, come back here. The cycle completes, right? That means 2-stroke engine. 4-stroke engine, there are 4 strokes that you need to run 4 stroke to complete the cycle, right? Then this volume, when the piston travels from bottom dead center to the top dead center, the volume that displays, we call this one as a displacement volume, right? Volume that occupy when the piston travels from bottom dead center to the top dead center, we call that one as the displacement volume, right? Then the volume at the top dead center, this volume we call as the clearance volume. So this is the clearance volume, right? The remaining volume when the piston moves all the way up to top dead center, we call this one as the clearance volume, and volume between the top dead center and bottom dead center we call as the displacement volume, right? I hope you are familiar with the terms like engine capacities. How we can categorize the engine is according to their capacities. For example, let's we talk about some of the motor bicycles, right? I'm sure you are familiar with, let's say, Discovery 1 to 5, right? There's a bike produced by the Bajaj company called Discovery, right? So Discovery 1 to 5. So what is this 1 to 5 means? Let's say Pulsar 180 or Pulsar 220. Let's say 135. You are familiar with these terms now? What does this mean? For example, Discovery 1 to 5 means this displacement volume is 125 cubic centimeters, right? 125 cubic centimeters. That is what is mean. That means the engine that used in that bicycle has a displacement volume of 125 cubic centimeters. That's what is mean. In some of the larger vehicles, for example, is cars and van, you may find something like some badges saying that 2.2 L. L for liter, 2.2 means 2.2 liters of displacement volume will be there on that engine. That's what it means, right? For example, let's say you have a car that displays 1000 cc, cc for cubic centimeters, 1000 cc engine. What is this? And it has four pistons. Then what this means? You have each piston displays 250 cc of cubic centimeters of volume. Into 4 you get the 1000 cc engine, right? So this is a multi-cylinder engine. That's why you have 4 piston. Each of that one displays 250 of volume. Then multiplied by 4, you have 1000 cc engine, right? That's how normally we refer the engine capacities, right? So displacement volume, clearance volume, top dead center, bottom dead center, straw, and the bow. Bow is basically the diameter of the piston. Okay. So this is how it basically look like inside the engine. So you have the crankshaft here. So the crankshaft, there's a crankshaft. Then you have the connecting rods, right? Connecting rods connect the piston. So this is the piston, and you have the cylinder here, right? Cylinder, and you have the exhaust valve and the intake valves, right? Okay. Then you have this is the intake manifold where the air and fuel comes in like this, and this is the exhaust manifold where the likewise, okay, where the exhaust goes out, right? And in this particular one we have a carburetor. So this is a carburetor. What the carburetor basically do is mix the fuel and air, right? Okay. Some of the engine have injectors, of course, right? And this one has a carburetor, right? Most of the motorcycles, motorbike, has carburetors, and most of the cars and other vehicles you have injectors, right? That's not come under this session, but of course for the general knowledge, right? Then let me talk about four stroke engines. So there are 4 stroke, as I said. You have the intake stroke, compression, combustion, or the power stroke, or then you have the exhaust stroke, right? So what happened is in the intake stroke, when the piston start from the top dead center, when it goes down, right? When it goes down, your intake valve opens, the air fuel mixture come into the cylinder, right? When this goes down, it creates a vacuum. Due to that vacuum, your air and fuel mixture, you have mixture here, comes into the cylinder. We call that one as the intake stroke. Then you have the compression stroke. That means both valves are closed. In this case, this one is open, this one is closed, right? So this one closed, this one closed. Then your piston moves upward. You are compressing the mixture, right? That means you are increasing the pressure. When you compress, it will increase the pressure, right? Then we call that one as the compression stroke. Then after compression, when the piston moves to TDC, right, ignite the spark plugs. What you have is spark plug. You ignite, you give a high voltage, supply a high voltage, then you ignite the mixture. Then you have the power stroke. Then that means when after you igniting the thing, your pressure increases, temperature increases, therefore that drives the engine and push the cylinder downward. Then we call this one as the combustion stroke or the power stroke, right? Then at that time also both valves are closed, right? All the valves are closed. Then you have the exhaust stroke after power stroke. uh, exhaust valve open, this one closed, right? Then you are pushing the piston upward, where all the flue gases exhaust will be directed to the silencer, right, or the exhaust port. We call exhaust stroke, right? So these are the 4-stroke. And again, I have a video here. I have given the link also. I want you to stop right now and observe these videos, right? It's basically explained all the strokes, right? Intake, compression, power, and exhaust stroke, right? I'm not going to run it in here, but I strongly advise you to go and check this video, right? Right. Again, then we have 2-stroke engine and 4-stroke engines, right? Again, that is not comes under our scope, but for the general knowledge, it's better you understand what this means, right? So you can refer more knowledge about that one if you refer this link, right? But this video, let me run this video right now. So I want you to identify what is 2-stroke and what is 4-stroke, right? Basically, if you listen carefully on the sound of that engine, you can basically guess what is whether it is a 2-stroke engine or a 4-stroke engine. So let me run this one. Right, I hope that you guys able to listen to the sound, right? So there are 2 type of sounds, right? Basically, the first one is a 2-stroke engine, sound of a 2-stroke engine, and the next one is the 4-stroke engine, right? If you observe carefully, of course, you can determine whether it is a 2-stroke engine or 4-stroke engine just by listening to the sound, of course, right? Right, of course you can find more information on this link, right? This one, okay? But again, it's not mandatory, right? It is for the general knowledge, right? How the 2-stroke engine works and what are the advantages, disadvantages. Likewise, you can find it in this video. Okay. Right, then few terminologies, right? We call something called compression ratio, right? We can derive something called R. R is the compression ratio. It's the ratio between the Vmax divided by V minimum. So Vmax means the volume at the bottom dead center divided by volume at the top dead center. That's mean like when you have a piston like this, right? Okay. So this the, let's say our piston in here. So this is bottom dead center and here is the top dead center. When the piston moves the top dead center, all the volume in here divided by the volume in here, right? Called the compression ratio. Volume at bottom dead center divided by volume at top dead center, we refer as the compression ratio, right? Then there's another term we call mean effective pressure, right? Mean effective pressure is the pressure that is equal to the net work that we can get from a particular cycle. So let me explain. Now let's say we have PV diagram and this is a particular cycle, right? We have a cycle and this is the net amount of work, right? W net we can obtain from that cycle, right? And we know that cycle operate in between the TDC and BDC, right? You have Vmax and V minimum, right? So what's the MEP mean effective pressure means what is the pressure, right? The pressure that gives same amount of W net, right? That means this area is equal to this area, right? What is the mean effective pressure? The value that gives the same amount of network as in that particular cycle. For example, let's say a particular question says you get 100 volt output, right? Then what is the mean effective pressure? Mean effective pressure equal to 100 watt divided by V max minus V minimum. That is what is mean. Some of the question you may be asked to find the mean effective pressure. Then this is how we can find the mean effective pressure. Okay. Then again I have a video for stroke engine explaining the four stroke engine and of course some additional knowledge, right? But again I'm not going to play this one in here. If it is in the classroom I would have played this one, but right now you can pause the video and go to this link and observe that one, right? Okay. Then we can come into our first cycle, first application, right? We call the application cycle. The first one is Octto cycle. So it is the Octto cycle that's run in the petrol engine. Normally most of the petrol engine you can find the Octto cycle. Okay. Now there are two type of cycles. Now what you seen in here above is the mechanical cycle. So this is the mechanical cycle, right? Okay, so this cycle, and what is this is a thermodynamic cycle. Okay. Now let's first we try to understand the mechanical cycle, right? Then we later on we come back to the thermodynamic cycle, right? Now we have four-stroke engine, right? Now we will start with the first we start with the intake stroke, right? Okay. Now what happened in intake stroke? So you have the intake stroke here, right? Now during the intake stroke, the intake valve is open while the piston goes downward, right? Okay. Now what happens when the piston goes down? It creates a vacuum, right? Now you are opening this port to atmosphere. So in atmosphere you have 1 atm, right? atm, and you are opening the cylinder chamber to atmosphere. That means you have 1 atm in here, right? At the beginning of the intake stroke, right? So let me draw this one the same time in the PV diagram. So you have 1 atm here, right? So this is 1 atm and you are in here, right? When the piston moves down, right, it creates a vacuum, right? It creates a vacuum, and to fill that vacuum your air, normally the air comes in, right? Therefore when the piston moves from TDC to BDC, right, you have a vacuum there. That means you start from here, you goes all the way to BDC, from TDC to BDC, since you have a vacuum there. So this is the 1 atm line and you have a vacuum there, therefore this line goes slightly below the 1 atm line, right, up to here. That is the intake stroke, right? Then so let's so this first, right, intake stroke, and this second, compression. Now what happened during the compression? Both valves are closed, this one closed, this one closed, and you are compressing it. Therefore what happened? Your pressure increases. Therefore you start from here VDC, your pressure increases, right, up to here. When the piston moves to TDC, from BDC to DDC, your pressure increases. That is the compression stroke, right? So you have intake stroke, then compression stroke, up to here. After compression, what is do? We ignite the fuel mixture using a spark plug, right? So at that point, so your piston still in the top dead center, and you are igniting the fuel. then it catches fire quickly and your pressure increases suddenly your pressure increases. That's why when you are here, your ignition start, then your pressure increases, right? But your volume does not change. It's not going to change the volume, right? You are still in the TDC, right? In here TDC, in here also TDC, but this one is the combustion. You start combustion here, so up to point here, that is the end of combustion, right? Okay, then what will happen? The piston moves downward, power stroke, right? That means we are expanding, that means volume increasing, and at the same time pressure also reducing. Therefore, we have the expansion or the power stroke up to here until you get to the VDC, right? Then after come to here, you open the exhaust valve. You have some pressure here. You open the exhaust valve. Once you open, your pressure drops. Right? After opening the exhaust valve, your pressure drops. Then you move the piston upward, remove all the exhaust to atmosphere. Right? That is, therefore, you are removing. That means you have higher pressure, slightly higher pressure compared to atmospheric pressure. Therefore, you start from here all the way to here. It's an exhaust stroke, right? I hope you understand the mechanical cycle, right? But when we come to the thermodynamic cycle, it's quite different, somewhat different, of course. But you can see the similarity, right? So if you start from here, right, from there all the way here to there, you can see it in here as well, right? Okay, right. Now we have Q in, right? We fire our fuel mixture, ignite the fuel mixture. That means basically we are adding heat. But Q out, right, we can't actually achieve in thermodynamic cycle in practically, right? What we doing instead, we replace the volume, right? That means when you come to here, you have exhaust filled with in our chamber. What we going to do, we remove that one and fill the cylinder with fresh air, right? So that process, so basically this process we can consider as a heat exchanging process, right? Okay. But what actually happened is you remove the air that is used, that means basically exhaust, remove that one, fill that one with exhaust, fill that one is fresh air, right? So that part from this point onward, from here all the way to here, removing of the exhaust and then filling with fresh air up to here is omitted in thermodynamic cycle, right? Instead we go from here to here and we denote this one as a heat exchanging process. Basically we say this is Q out. Okay, that's what you see in here. Okay, therefore this is where the fresh air fill in, right, and this is where the exhaust is out. Therefore when you come to thermodynamic cycle, we omit these two things, right? Okay, now let us start from the compression from this point, right, from this point onward, right? Which is why, because it is ideal to the mechanical cycle as well, right? So we are compressing it one, so we call this one as the we are compressing this one from 1 to 2. We are compressing this one. That's means we are isentropic compression, right? To start from here, isentropic compression, right? Then we ignite the fuel mixture, right? Then that means we are adding heat. At this point we are adding heat. Therefore this is we call as the constant volume heat addition. This constant volume is not going to change, but we are adding heat. Therefore constant volume heat addition, right? That's mean this one, right? Okay, we compress the thing, right? We add the Q, add heat, right? Then then we expand the thing, isentropy expansion, right? Expand the thing, isentropy expansion, then, right, then what we do, we Q out. This is the heat exchanging process, right? We call this one as constant volume heat rejection, right? So this is constant volume heat addition, this is constant volume heat rejection. Then we have isentropic compression, isentropic expansion, right? Okay, those are the 4 processes. Okay, right. So this is the PV diagram for the Octto cycle, right? The same thing we can draw in the TS diagram also. So you have the PV diagram, right? So you have the in here you have isentropic compression. Why it is isentropic? Because entropy change is constant, right? Then you have constant pressure, constant volume heat addition, isentropic expansion, right? And constant volume heat rejection, 4 to 1, right? So if we can draw the same thing in the T and S diagram, right? So 1 to 2 is isentropic compression, therefore there is no entropy change, therefore we can derive 1 to 2 here, right? Isentropic expansion, isentropic compression, then constant volume heat addition, right? Then isentropic expansion, constant volume heat rejection, right? Okay, right. So let me derive the equation for neta, right? So Q in, so this Q in, this we are the Q in, right? Q in, 2 to raise the Q in, again same in here, the Q in, right? Okay, so we can write Q in equal to U3 minus U2. U means internal energy at point 3 minus internal energy point 2, right? Same thing we can write CV times T3 minus T2. CV means specific volume at constant, specific heat coefficient at constant volume, right? CV is for constant volume specific heat coefficient, right? Okay. Then Q out we can write U4 minus U1. Again we can say CV times T4 minus T1. Right? Then we can derive the neta Octto cycle equal to W net divided by Q in. Then we can write the W net as Q out, Q in minus Q out, right? W net, we can write W net equal to Q in minus Q out divided by Q in neta. Then we can derive something like this, right? Neta equal to 1 minus Q out divided by Q in. Then for Q out and Q in, we can substitute from this equation, right? This one and this one. Then we can write, so the, if we substitute from this one, CV goes off, right? This one cancel out. Then we can say 1 minus T4 minus T1 divided by T3 minus T2, right? Then again we can rearrange this one such a way that we can get the T1 out, right? From this equation we can get the T1 out, and from here we can get the T2 out, right? Therefore we can come across something like this. Okay. Then for the process 1 to 2 and 3 to 4, we can derive something like this, because 1 to 2 and 3 to 4 are isentropic process. Therefore we can say T1 divided by T2 is equal to V2 divided by V1 into the power K minus 1, right? What is K? K is the specific heat ratio. That means Cp divided by Cv, right? Okay. So so remember Cp is the constant volume heat, specific heat coefficient at constant volume, right? Cp, Cv. Then Cp means specific heat coefficient at constant pressure. So this constant pressure specific heat coefficient, this constant volume specific heat coefficient, right? So the ratio is between that one is we can say K, right? Cp divided by Cv is the K, right? Then with that equation we can substitute for T1 divided by T2 for this particular equation, right? Okay. Therefore we can write neta octo equal 1 minus 1 over Rk minus 1. R is compression ratio, K is the ratio of specific heat coefficient, right? So we can come across something like this. Okay. Now what this equation means, right? Now neta, the efficiency of Octo cycle depend on R and K. These are constant, this is a constant, this is a constant, R and K, but K also a constant, right? K also a constant because it is Cp value, Cp divided by Cv. Cp is a constant, Cv is a constant, therefore K also constant. R is the only variable we have in this equation. R equal for compression ratio, right? Now according to this equation, when the R goes up, your neta goes up. So what we like to have is to higher efficiency. If the engine give a higher efficiency, that's what we need, right? To engine, if you make a higher efficiency engine, what the thing you should do is you increase the compression ratio, right? Isn't it? Okay. Now that means compression ratio equals V max divided by me minimum, right? That's when your piston goes like this, right? So this V minimum and this V max, right? So this V max, this V minimum. So what we can do to increase that one, either you can increase the bore diameter, right? Diameter, or you can increase the stroke. Either increase this one or either increase stroke, right? If you increase either of this case, you can increase the compression ratio. The increase in the compression ratio means you can increase the efficiency, right? But so for this the graph for the compression ratio, you have the compression ratio here and you have the efficiency in here. So this is how the graph goes, right? So we can see higher the compression ratio, higher the efficiencies are, right? But in normal situation or the practical application, that means all the petrol engine you can we have in today is limited to 7 to 10. So maximum you can achieve is 10. There are no petrol engine that has a compression ratio beyond the 10 as far as my knowledge, right? There are some engine, very rare engines which has a compression ratio up to 10, right? Up to 10. Some of the direct injection engines, there are very few engines that has a compression ratio 10, but most of the time you can have 9.5, somewhere in between, right? So all the engines, most of the engine, the compression ratios comes under like this 8.5 to, let's say 8.5 to 9.5, right? Now why we can't increase this one, right? What's the problem, right? If you increase the compression ratio, of course we can get a good efficiencies, isn't it? Yes, right? So the problem is when you increase the compression ratio, it tend to increase the temperature, it tend to increase the pressure, and that high temperatures and high pressures engine create NOx, we call NOx, NOx. X can be either 1, 2 or 3 likewise. What is this NOx means? NO or maybe NO2 or maybe NO3 NOx. What's happened? Oxygen react with nitrogen and it create NOx. These NOx combine with H2O, right? H2O, and it create acid. Actually H2NO3 likewise, right? So it create different acid. That means when you do burning inside the cylinder, it create acid. Now what happens if you create acid? This acid react with the metal. So engine body, piston, everything is metal. So it react with the metal and it decay the metal, right? That means if you increase the compression ratio, your engine will decay and engine will damage very quickly, right? So you can't have engine last for long time. It will damage your engine. Therefore, to omit this one, manufacturers limit their compression ratio up to 10, right? Okay, but if you compare this one with the diesel engine, right? Diesel engine, so this is the normal ratios for petrol engine, but if you compare this one with diesel engine start from somewhere 14, can go up to 18, right? Therefore a diesel engine has a much more higher efficiencies compared to petrol engines, right? That's why most of the heavy vehicles, right, lorries, buses, right, container prime movers, ship engines, right, all the heavy vehicles use diesel engines, not petrol engines, because they are much more economical, much more efficient than the petrol engine, right? So we will discuss that one in more details when we talk about we talk about the diesel engines later on, of course. But for the time being, diesel engine has much more compression ratio. Therefore, their engines are much more efficient than the petrol engines, right? Okay. Right. So the next thing is the question. I will make a separate video for the question as a tutorial lecture. Then you can work on this question at there, right? For the time being, let me stop right now. Okay.